you very much for coming, everyone. It's great to see you here. Today I have the great honor to sort of pre-introduce, or introduce in a weak sense, introduce Dr. Chen Rizzo from IBM, head of IBM Research Collaborations, to speak about why she cares about integration. So this is a really interesting topic, and we've got a really great speaker. And
all right, thanks, Daniel. Thanks for the introduction. So one thing about me is that today's my birthday, so happy birthday to me. And thanks. Speaking of when I was born, I was born in the U.S., but I actually moved to Singapore when I was 5, and I actually lived on the NTU campus for the next 12 years before going back to the U.S. So when I left NTU, there were only 7 residence halls, and now I don't know how many there are, at least 20. But it's really nice to be back. I came back last year, and I'm working now with the research collaboratory here. Oh, it's not? And our research collaborator here is really a branch of our business analytics and math sciences group that is headquartered in the U.S. And our goal is to see how we can be using mathematics to help primarily the Singapore government address problems that are of interest to them. So that's where the group that I'm in general. But I'd like to talk about why integration factors into the work that IBM does and why I actually care about it. I mean, you'll see that there are a couple of steps to get from integration to what I actually care about. But for most of you who are in your first year of undergraduate studies, I think this is the time for you to really get those fundamentals down, and eventually when you come to your 37th birthday, you will be glad that you paid attention now, because there are too many things going on later on, and it's hard to get back to the details again sometimes. So here's I thought it was interesting to think, there are 2 definitions, more than 2, but at least 2 definitions of integration. And lately, with all the buzz around Singapore, around the population growing and people coming from different countries, I like integration because it is about people getting along together and the mixing of cultures and different backgrounds. So that's one reason already why I care about integration. But from a mathematical point of view, let's think about what integration is. It's a process of computing an integral, for example. And just a very simple way to think of it here is if you're trying to compute this expression over here. So just to ground us on what we're talking about. And I'm trying to keep this very high level because it's supposed to be a fun talk. And we'll see this, again, reflected very much in how we work with probability. Okay, basically, you're trying to compute integrals over certain ranges. And the challenge in probability theory is what is this function f? And how do we compute this function f? And sometimes we can't necessarily write it down. So we have to use numerical methods. And in the real world, which is uncertain, and we have to try and estimate what this function is, it's actually a very, very practical problem. So here's just a little joke here about random numbers. So over here we have our random number generator, and it's generating 9, 9, 9, 9, 9. And the question is, are you sure that's random? And even though 99999 sounds like it's not, ultimately you just can't really be 100% sure. And what I'm interested is really understanding what the risks are. Because I don't feel comfortable when I make decisions, or politicians or presidents make decisions on my behalf based on their gut. Right? I think that they should be using data to properly estimate probability distributions, and then their judgment comes into play in terms of how much risk they're willing to take. And they shouldn't be just using their gut to estimate what the risk is, right? So we should be objective about what the risks are, and then we can be subjective about how much we're willing to tolerate. Okay, so I don't know if you guys have really talked about or taken probability classes yet, but probability density functions, I've heard of the normal distribution, but there are many other different types of kind of popular distributions that we use to represent the chance that a random number will turn up to be some value. And there are some interesting, sometimes, relationships between them. For example, if you take two exponential random variables and add them together, you get a gamma distribution over here. Okay? And these distributions often correlate to certain stochastic processes in real life, like how many times should you flip a coin before you get how many times do you get a tails before you get a heads when you flip a coin? So that corresponds to the geometric distribution. So there are a lot of interesting processes in the real world that display some of these classic distributions. Okay, so why am I telling you about that? Because I'm trying to make the link again back to integrals, right? Well, suppose that you have x, which is a random variable, with some probability density function. As shown in the previous chart, it could take different shapes. Those functions have to have certain properties, which I won't get into. But ultimately, if you wanted to compute the probability that this random variable x, when realized, will lie between some value a and b, you're computing an integral expression, right? And so the more complicated the process that you're trying to represent, like I said, the challenge usually is in what is the expression for p? Can we even express it analytically? And then computing the integral. So I hope it's kind of obvious here that if you're working with probabilities and trying to compute probabilities, you're going to have to understand that integration is fundamentally at the heart of that. Okay, so I just want to take it maybe a little step more complicated than that and talk about the sum of two independent random variables. Already this is still very simple because I'm only talking about two random variables and I'm saying that they're independent of each other. Right? So suppose that, again, in a simple example, I say that I'm going to roll a die. It's going to be uniform between 1 and 6. Then I say I'm going to roll 2 dice. So what's now the distribution of the sum of those two, the values on the dice, right? So I've got two uniform random variables between 1 and 6. It's not continuous in this case. But how do I compute the distribution of the sum? Do I know that it's going to be uniform as well? Is it going to be uniform as well? So, for example, let's say z is the sum of two random variables x and y. All right, then it means that the probability that z takes on the value little z, some instantiation, will be the probability that the sum of those two variables, little x and little y, equals to little z. Right? But we also know that if z is equal to little z, and if x is equal to little x, then it should be true that y has to be z minus x. So if we want to know the probability of z, then it's really, since these variables are independent, we can actually multiply those distributions together. The density function associated with big X being little x, and then the probability that big Y will be the value z minus x, right? Because that will be the probability that z will be little z. And so we actually, if we think about this in the continuous realm, there's something called a convolution that is defined as shown. So if you have two functions f and g, so imagine that f and g correspond to the probability of x and the probability of y being z minus x that we saw in the previous chart, right? And in this last bullet item. Then if you see there that you have this function f, and then you have function g, but there's this little t minus tau, right? So that's the same as that z minus x bit that we had to do. So this convolution actually, if you were to compute the value of this function, you would actually get the expression for the density function for the sum of two random variables, right? And again, this is a simple case when you're just trying to add up two random variables, and I gave you before a simple example of rolling one dice and then rolling two dice and wanting to know the sum. In the real world, you're going to have, probably tens or potentially more, thousands of random variables that you may be adding, subtracting, dividing, and multiplying. So the expressions can get much more complicated. And the random variables typically are not independent of each other. Usually when we take one action, it has an influence on the distribution of some other variable. But sticking with the simple concept, here's a nice illustration I took from Wikipedia of how a convolution works. So what you're actually trying to do when you perform the convolution is you quite literally take two functions. So in this case, if they were both uniform, and you were to slide them across each other, as you're seeing here, what you're trying to understand is what's the probability, what's now the shape of the sum of those two variables. And you'll see here that when they overlap, you're going to take the area of overlap, and then the size of that area is being plotted in this dark black line. And so now you see that as you slide one function across the other, you get a triangle distribution, right? So again, this is for a very simple case of two square pulses being convolved with each other. But what if you want to convolve, an exponential distribution with a gamma distribution, or any one of these that I showed before? What if you want to convolve them with something else? So this exponential distribution that we see here, a lot of times they use that to represent the arrival rate of someone. So let's say if you're at a bus stop, they'll say that the number of people who have arrived, or the time between the arrivals of each person at the bus stop, is exponentially distributed. So, so as mentioned, these can get a lot hairier because random variables may not be independent. You may have to consider the joint distributions of random variables, and you consider the fact that when you measure a process, you're not necessarily going to observe that it fits into some, well-known distribution. It might be some bimodal, some weirdly shaped distribution that, like if you look at custom over there, right, where you're not necessarily able to characterize very easily. Okay, so okay. So this really is the link that I'm trying to make between integration and probability. And what I want to talk about next is really how, from an IBM point of view, we're feeling that having a very solid understanding of probability is going to be important to our clients. Okay, and from the point of view of the Business Analytics and Math Sciences Department at Research, which is the largest math department, industrial math department in the world, we have over, I think it's 150 people working on math. Not everybody, but a good portion working on math that will allow IBM to create tools that will make it easier for our clients to have a competitive edge, because they're better able to make better decisions in the face of risk, right? As I said, unfortunately, a lot of people who are in positions of power today, I'm not saying they're bad people, but they may not have had a lot of technical math training. And even if they did, they may not have really paid attention in class to integration or studied probability theory. And it's true that no matter how clever you are, as humans, we have certain limitations in our abilities to react quickly and correctly in certain situations. So there's an example that I'll go through in a second, just to kind of, well, we'll see how you guys respond, but it's easy for our intuition to fail us, and it's not an indication necessarily of our intelligence, but sort of the way our brains are wired. And so again, why do I care about this stuff? Because I think that if we want to take advantage of the fact that there's more data available now, and we want to take advantage of math and computers, we have to be willing to admit that in some ways we're not as clever, right, as the science. And we have to be willing to say, well, I'm more likely to make a bad decision in this situation. So even if the math suggests an action that is not what I would have first chosen, that I sort of trust the science. Right? If we're unwilling to take that step, then we'll never do better than what humans are capable of, in some sense. I don't want to get all philosophical, but and it's only going to be when, say, people like you have enough influence on people who are making decisions, or are the people making the decisions, that will start, taking that step forward. So, the goal is to really not only provide tools that make it easier for people to make decisions in the face of uncertainty, but also to start spreading the word and have more people out there who can appreciate and recognize the value of math, really, and feel comfortable with it. So I've used this chart before. I don't know if you guys were at the talk when I was here, but IBM is still an IT company, right, information technology company, so it's important to us to understand what kind of data our clients are having to deal with. And while people have often talked about how there's a large volume of data and how data is now being generated very quickly and we have to manage the data in real time, and that data is coming in all different kinds of forms and formats, so that's sort of well known. But as a fourth dimension, we're really concerned about how people are now dealing with the uncertainty associated with that data, the veracity, right? So this links to probability. Just because we're uncertain about what a piece of data is telling us, does that mean that we should not use it at all, right? It really is about saying, okay, how sure am I that this piece of data is telling me A instead of B? And then if I can have a good sense of how sure I am, then, like I said, that's where the judgment comes in, and you decide whether it's a chance you're willing to take. And the uncertainty here in the data can come from many different sources, right? One can be that the process that you're measuring itself is by nature uncertain, and we want to understand what that looks like. And some of these processes are natural. Some of them may be man-made, for example, in manufacturing. But until we understand every single thing about physics, it will remain in some sense to us, unknowable. And we want to capture the extent to which we don't know it, to put in one way. But then the other source of uncertainty is the way that we measure things. Right, so when we're trying to understand where a car is located, for example, the GPS signal or the result, the coordinate is not 100% precise, right? So there's some uncertainty associated with how we measure things. When we try and interpret text that we read on the internet, there's some question as to whether or not it was a typo, whether or not it was being used in a certain context, or whether or not we're interpreting it correctly. So there's uncertainty there as well. That just is a couple of examples. And then there's a third source of uncertainty, which comes from the models that we use to make decisions or to make predictions. For example, we may assume that, okay, let's assume there's a linear relationship between these two variables instead of a nonlinear one. And all these assumptions that we put into our models also contribute to any variation that we may see in our results. All right. So why do I care about integration? Because I care about making smart decisions, and that's a very human thing. And we all make decisions in an uncertain environment, even though we may sometimes pretend that we know what's going on. And in certain situations, we do have a tendency to be wrong about the way that we make decisions, systematically wrong about these things. And psychologists and other people have measured and studied these things and found us to be systematically wrong in certain situations. However, if we understand and can trust mathematics, probability theory, of which integration is an integral part, we can start to leverage the value of information in this new era where there's an abundant amount of data. And what I've observed in working with clients is that there's a lot of hesitation sometimes in using models because using mathematical models because they don't really understand the underlying theory. So let's test your intuition. Have you guys heard of the Monty Hall problem? Have you done it in class already? Okay. All right. Okay. Well, I mean, I've heard it before, and every couple of years, whenever I come back to it, I still do it wrong. Anyway, so I'm just going to pull it up here. So this is the Monty Hall problem. Let's play. All right. So here's how it's set up. There are 3 doors here, and behind the doors there are, behind each door there's either a goat or a car. All right, and I'm telling you that there are 2 goats and 1 car. Okay, so it's either car, goat, goat, car, goat, or whatever, but you don't know. And obviously you want to open the door with the car, because if you do, then you win the car. And if you open the car with the goat, then you can take the goat home. All right, so the way this works is that we first pick a door, and but before we open it, okay, so I'm going to click on a door, say the middle door. All right. Now, before Monty Hall's the name of the game show host. Before he opens this door for you, he's going to say, okay, you pick this door, and you hope that it's a car behind there. But let me increase your chances of picking the right door. I'm going to give you an option now. I will, of the other 2 doors, open one of them that I know has a goat behind it, right? And I'm going to give you a choice now. Do you want to stick with your same door, or do you want to switch to the other door? Okay, so he'll say, all right, well, you pick the middle. Now I'm going to tell you that there's a goat behind this door. Now you want to stay with the door that you have, or do you want to switch doors? You don't care, or what would you want to do? Okay, how many of you would stick with the same door? Okay. How many of you would change doors? Okay. All right. So more people said that they would switch. Okay, Zong, you get a goat. Okay, but this is not that you are wrong. It's about the strategy, right? So it's about, and this is another thing probably. It's how many chances do you get to keep playing this game. So that's why they're keeping score over here, because so they're saying try again. Okay, let's just do it one more time. So say I pick this, and then I'm going to switch. Okay. All right, I get the. So I played this game twice, and once I won, and the other time I lost. Right? And the question really is, which strategy is going to increase your chances of picking the car? Right? Is this the strategy of switching doors or keeping the same door going to have a higher probability of picking a car? And okay, so those of you who decided to stick with the same door, which were all the ladies, why did you think that you should stick with the same door? Okay, all right. Well, okay, so let me tell you why a lot of people will choose to stick with the same door, right, including myself, depending on the day. It is that you figure, okay, well, there's 2 doors left. He's already opened one with a goat. So there's a 50-50 chance that, these doors, one will have a car, one will have a goat, right? And I don't know which one it is, so whatever. I might as well just stay with the one that I have. Even if I switch, it's the same thing. I could switch or not switch, but I'm happy to stay with the current choice. And so that is a sort of a natural response of a lot of people, which is actually a lower probability strategy than switching doors. Because it turns out, and if you want to read this, you can read how it works, but it turns out that you're actually getting more information. Because when you've picked one door and Monty Hall has to pick another door, he is constrained to pick a door that has a goat behind it, and he knows where the car is. So actually, if you pick the right door to begin with, and the other two doors had goats, then Monty Hall can pick either door. But if you picked a goat, now Monty Hall cannot just pick any of those other two doors, right? He has to make sure that he picks the door that has the goat. So once he does that, he's actually sort of giving you more information about where the car should be. And so so already now you know that, okay, in the case that there was a car, then he's actually picking in the door with the goat, so that means the other door must have the car. So it's actually to your advantage then, if you repeat this game over and over, to switch doors, because he's sort of telling you by opening the door with the goat that the other door has the car, if there's a car there. Okay. But that's only in the case where you pick the door with a goat to begin with. Right. So, I mean, again, it's not obvious, and again, I bet if we had more people in the room, we would have seen half the people switch and half the people not switch, or maybe more people choose the intuitive but incorrect answer. Right. Anyway, this is like a classic example. So if you ever become teachers one day, you can also put this in your class. It's a classic example of where a correct answer doesn't make sense or feels like it could be wrong, and humans tend to make mistakes when they're trying to assess risk. All right. Okay. So some of the applications of probability that we use, and I'm just going to go over like 3 of them. So one is in estimating similarity between two distributions, and that's something that we do a lot in many different contexts. So some of these examples are not all IBM examples. They're kind of just general examples. But there's something called the Earth mover's distance, which is really a way of measuring the distance between two probability distributions. Why they call it the reason they call it Earth mover's distance is they try to measure if I have 2 mounds of dirt. So if you think of 2 probability distributions, how much the distance between these 2 distributions or mounds of dirt is the amount of work or energy it takes me to transfer to make one pile look like the other pile. So how much dirt and over what distance must I carry each grain of sand from one pile over to the other side in order for me to move this pile so that it looks just like the other pile. And so in the context of understanding how to interpret cell phone data, to understand what route someone is traveling on a road network, where the road network may be quite dense, one can look at the distribution of signals that are being received from the cell towers and maximize the likelihood that if I see this sequence of communications between the caller and these cell towers, that it's most likely that the route that this traveler is currently traveling on this sequence of roads, right? Because I'm trying to understand, for example, from the cell phone records, what are the routes that people travel on the road network. Okay, so if I understand that to get between point A and D, a lot of people choose this route versus another route, then I can better plan for my transportation infrastructure. I might also be able to better implement incentives to manage congestion. Okay, okay. And this Earth mover's distance is also used to in image retrieval. So where they need to know whether or not 2 images are similar to each other. So if you take a certain property of a picture, say brightness along a certain color dimension, you end up with some distribution, right? And you want to know whether or not two pictures, so your algorithm doesn't see the picture, it sees these two distributions. And so what's the chance that how far apart are these two distributions? Okay, and we can use the Earth mover's distance to compute these kinds of measures and determine if we believe that these two images are similar enough that we will say, these are pictures of the same thing. All right, so that's another application of probability and distributions. Okay, so one topic that is of interest to IBM lately is that of creativity. So can a computer be creative, right? Or are only humans capable of that? So when a human looks at a set of ingredients and creates a recipe, a very delicious meal, they use their creativity. But could a computer compete with a human on that level? Take a bunch of ingredients, tell someone how to put them together, and concoct a dish that is more tasty than the best chefs in the world? Human chefs. Right? Same thing in the second example here. Suppose that there are a bunch of features. So like ingredients, you say features of that people find desirable in a device. Like I want to be able to do email, I want to be able to navigate, I want to be able to talk on the telephone, I want gaming, and so forth. And then the engineers at Apple kind of invented and came up with this creative design for a device that could do all these things. Right? If I had given these same preferences to a computer, would it have told me, oh, you need to build a device that looks like this and has these things in it? Right? Could computers be capable of that? So how does this link to understanding probability? Okay, let me give you one more example first. Another is, can a robot be a painter? Like if a robot only knows certain elements, can it put things together and create an image that is comparable to one that a human would create? Would we deem it to be an act of creativity? Okay, so this picture that you see on the right was created by a robot. And so there is some method, as we say, to the madness. And there are three elements that we're looking at, right? One is something, and this is not my research, so I admit that I don't have all the details on this, but one element where we have to develop methods for is understanding element prevalence. So if we think of elements as, for example, ingredients or combinations of ingredients, so can we understand in popular recipes which combinations of ingredients tend to be more prevalent? And those may be the kinds of combinations that we'll want to use in a computationally creative recipe, for example. So here it's really about estimating and understanding what joint probability distributions are that we want to use to be novel. Okay, and how do we assess what novelty is? So if something is novel, then it shouldn't be very common, right? So the probability of it occurring should be low. And then there's this notion of Bayesian surprise that actually I don't really understand too well. But my message to you here, right, is that in trying to do some of these neat things and trying to see if we can make a computer become creative, there are elements to it that don't necessarily involve probability, for example, the optimization over there, although sometimes optimization is stochastic in nature. But a lot of it is about understanding the underlying process and being comfortable with things being uncertain and characterizing that uncertainty. And then really you're trying to maximize the chances that you'll come up with something good. So I won't get into the details, but I'll just show you that okay, there's an integral in here somewhere in Bayesian surprise. Okay, so when you want to work out and compute all these things, when you want to compute probabilities, you're going to be doing it either numerically, okay, or analytically. All right. And then I want to take a slight turn in this last application area. So another reason why I care about integration, I would say, is that I care about people, right? And we are doing this in IBM research in Ireland, which is we're thinking about what are the most effective ways of communicating probability, right? Because we can't expect everyone to be interested in math or to understand math. But those of us who do, we can make an effort to meet other people halfway and help them to make better decisions, right? By not having an attitude that says that, well, if you don't understand or appreciate math, then you deserve to make poor decisions, right? About your health or about your life or about your family. So there are people, psychologists and other people, who are doing research to understand how we can present information to people that makes them more likely to have a correct intuition and understanding of what the risks really are to them, right? If you're trying to tell them, like, you really should stop smoking because your probability of getting cancer is X and whatever, you hope to convince them, not by lying to them, but, by really helping them understand what risk they're facing. So for example, people have found that if you're telling them what their chances are, you shouldn't use very small denominators. So somehow communicating that a chance is 10 out of 100 is better than saying the chance is 1 out of 10. Okay. And displaying visually, for example, how many people, in red versus the other, blue, it's actually, I think they're actually saying that it's good to group people who are in the red next to each other, but at the same time they discovered that if you want people to better understand to appreciate that it's random, that if you kind of spread them apart and distribute them, they'll get a sense that it's okay. There's some. It has a stronger conveys the idea of chance a little bit more strongly. Ouch. Some people also found that if you're helping them to visualize chance, that you may want to, for example, use length rather than volume. So using these bars rather than the circles, it's easier for them to understand risk. And when you're trying to help people understand what their risk is relative to the general population and give them a sense of how their behavior may actually lower their risk, there are a lot of different ways that you can decide to present this to them so that they ultimately, hopefully make a better decision. And why do we care as IBM? Because after we've done all the math and computed all the right numbers, if we can't communicate it to the users in a way that encourages them to make good decisions, in light of the risk that we've spent all our effort computing for them, then we never really will see the impact of that, right? So it's really about making sure that you get the fundamental math right, all the way to the point of bridging the gap between the math and the people who don't quite get the math, right? But they're the ones who are making the decisions. So with that, really was all I wanted to share with you on why I care about integration. This connection to understanding probability, computing probabilities, and why being more rigorous about probability is important in decision making. Part of it is that as humans, we have limited capacity to correctly intuit risk. And part of it is that to estimate risk can take a lot of computational power, right? Ultimately, we are making decisions in an uncertain environment. And the majority of decisions or models that people use today are deterministic models. I feel part of it is because people can very clearly trace back, 1 + 1 is 2, and blah, blah, blah. This is how I came to my answer. And when you're dealing in a stochastic environment, it's not so obvious how you got from point A to point B in terms of your decision making. But if more and more people are comfortable with probability theory, then we become a little more comfortable not knowing that, understanding that many paths are possible, many outcomes are possible, but we're trying to really maximize the chances that something good happens. So, yep. Yes, we do. I mean, what do you mean, like our company, as a company? Yes, we do.
Can you give an example of, a decision made by, according to your counsel, when you applied all this probability and everything, some actual decision made by a big company or a government. I remember you mentioned something about an event that happened when you worked in Ireland.
Okay, wait. So let me think. I don't have an example right now with a government, but I do have an example in finance. Right? So people want to know what are good loans and what are bad loans to give out, right? What are the clients that are going to be high risk or low risk? There was actually one of our clients, I think they were experiencing a problem in their IT system, right? They kept getting the same system error. And they weren't sure what was triggering it, and so they couldn't really get to the root of what the problem was. It turns out that we took data of what was happening in let's say, the 3 hours leading up to this failure, in the many, many times that this same failure happened. And of course, the path to failure was not always identical, but in the end, there's some pattern, right? That higher level pattern that identifies what led to that breakdown. And so one of our researchers analyzed that data. There was actually a large amount of data, and you really didn't really know where to look. And she knew nothing about IT systems. But she was still able to discover from the patterns what the most likely cause of that error was. And when they went there to look and fix it, they actually were able to stop having that system error, which, depending on the company, having a system error pull your system down, even if it's for 20 minutes, can mean a lot of lost business. So that's an example that. Yeah.
What kind of mathematical methods are used in pattern recognition?
Well, I think there is a lot of the similarity stuff. Like the Earth move resistance is just one way of determining if two patterns are similar to each other. And we're actually using it in healthcare, too, to decide if certain patients are similar to each other. So you look at medical records. Are these two patients similar enough to each other that I think that if I treat this patient, that the response from this patient will be like what that other patient responded to this treatment? It's not pattern recognition is not my area, but you can kind of Google it. But it would be closer to along the lines of the similarity type of methods. Yeah.
And left now. That is one question. The second was concerning communicating risk. So risk, sometimes risk depends on how you break it down. The Simpsons paradox.
Mhm.
So you can have treatment A is better than treatment B for kidney stones, but treatment B is better than treatment A both for small kidney stones and for big kidney stones.
Oh, okay.
So both of those things, how the Simpsons paradox is communicated and what else?
Yeah, I don't know how I should see if there are ways of communicating Simpson's paradox. I haven't actually, so I don't have a good example for you right now. For causality, I know that in certain situations, there's a method called Granger causality. It's not, again, not my area, but I know that researchers that are in our group have been using that method, again, so that with high probability we can identify potential causes. But and there was another area. Okay, I'm forgetting now. But no, I mean, I think you can never be sure that something is causing something else. But I think given the correct, under certain limited assumptions, you can be more, likely to identify causes of other things. But I have to admit, it's not my, yeah.
Thank you for a wonderful talk.
You're welcome. Thanks for your attention.